So, we need to work to ensure an adequate sample. This sounds simple, but unfortunately, the most common way scientists seek to do this can be problematic. One common approach is what is called run and check. You run a batch of participants, you check to see if the results are significant, you celebrate if they are, or you run a few more if they're not. You can then repeat this process until you either get what you wanted or give up. Sometimes run and check is conducted across grad students or postdocs. You can just keep giving the same project to different people until someone with good hands gets it to work. This is really common, but it's also deeply problematic. All the way back in the 1950s, Anscombe warned scientists about the dangers of this approach, calling it sampling to a foregone conclusion. When you run and check, you're leveraging sampling error. You're giving yourself repeated opportunities to capitalize on chance. It's like shaking the magic 8-ball until you get the answer you wanted. This produces biased research results, and it inflates the false positive rate. So please, don't use run and check. To protect yourself against it, come up with a clear stopping rule, a statement on when you will stop collecting data. Pre-registration can make this commitment public and verifiable. Another approach is to select a sample size based on the published literature. Well, our competitor lab used 8 animals for this assay, so we'll do the same. That can seem like a good idea, but unfortunately it is not. It is now well documented that in many research areas, sample size problems are pervasive. That means researchers are using sample sizes that are demonstrably inadequate. I'll explain what this means in a moment, but for now, what I can say is that if you plan based on what is published, you could be carrying forward the mistakes of the past into your future research. Let's look at the example of transcriptional profiling experiments like microarray and RNA-seq. There has somehow evolved in these fields a tradition of applying the rule of the triplicate. I think this emerged from early work where the techniques were just too expensive to collect more than 3 samples. But even though expenses have declined, there still seems to be a tradition of using the previously published literature to set sample sizes, and 3 replicates is amazingly common. This is actually crazy, because analysis is clear that this is not an adequate sample size for most applications. There's simply too much variation in gene expression across organisms and samples to generalize from just 3 samples per group. Reasonable power only starts to emerge with 5 animals per group, and in most cases will be optimal with about 10 biological replicates per group. This is really astounding. It means that much of what has been published using these techniques is actually worthless. So hopefully this has caught your attention. Do not plan sample sizes based on run and check or based on tradition. Both can be tremendously problematic.